Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 6.3.5, counting spanning trees. So let's look at a graph and let's see, how do we count how many different spanning trees it has? I mean, look at this last graph, right, that we were looking at, last example. This is one of the spanning trees, but there's a lot of other ones. I mean, how many are there? We can go through and sort through it all, but if it's a huge graph, we need to have a nice formulaic way of approaching this problem. So let's look at this example here. Let's, in counting the number of spanning trees, and try to do this in a way that actually uses matrices, like the incidence matrix, for instance, is what we're going to be looking at. Okay, so let's kind of look at what's written here. A spanning tree has three edges in it. How do we know that? Because it's one less than the number of vertices. So and this is a connected graph too, because you can't have a spanning tree in a graph that's not connected. Be a spanning forest rather, but because you have to have things connected in order to have a tree going throughout to begin with. Okay, so we're assuming it's connected here. Let's see, not every collection of three edges creates a spanning tree though. So so there could be less than depending on what the edges are doing in the graph, that is. And like for instance, oh, these three edges right here don't produce a spanning tree. So not every group of three does it. That's an example. But if you say from five, let's see, we have from five edges, we choose three, five choose three. I mean, there's less than 10. We know there's less than 10, so we keep that in mind. Okay. But really the only ones that we need to eliminate are the cycles that have three in them. And there's only two of them, and so that have three. So there should be 8 spanning trees. And we did that by just a quick calculation. However, we can't usually just do that because that was pretty visual. Let's keep going. Let's actually get the number 8 another way. So let's look at the incidence matrix. All right. The spanning tree occurs every time we choose 3 columns which have dimension 3. Okay, so every time you have 3 columns which have dimension 3, because we wouldn't have a cycle in there, right? So basically every time we have a tree of with 3 edges, that'll actually be a spanning tree. You can convince yourself of that idea, but even just looking here, I mean, every time you just have 3 edges together in some way that don't have any loops, you'll have a spanning tree. So that's kind of the idea. So we want to basically look for all the different sub 3 by 3 matrices in here that have dimension 3. All right. Now let's think about this for a minute. What if we were to subtract the top row out? If you got rid of the top row in this incidence matrix, we know exactly what's in it, right? Because the top row depends on everything below it. If there's a 1 and there's no negative ones, then there must be a negative 1 there. If there's let's see, and if there's a negative 1 and a 1 below it, must be a 0 up there. So the top row depends on what's below it in the incidence matrix. Okay. So now right here we were talking about 3 by 3, but I guess we can't have 3 by 3s if we just, so that's why we're eliminating the top row, because we only have 4 rows, right? So we can't really do that. So but we're looking for groups of 3 that have a dimension of 3, basically. So to do that, it's equivalent to just looking at 3 by 3s if we just eliminate the top row, and then the dependency here, if we have a dimension of 3 just down below, that's equivalent. So that just makes it a little simpler right here. Now finding determinants of a 3 by 3s in here. So there's lots of different 3 by 3s you could get. You could pick this column, or you can pick that and that column, right? You can pick different columns and put them together and work with them. Now, now in the incidence matrix itself, as we do this, is we pick 3 things and it happens to be non-zero because of our choices of ones and zeros and -1s, and it kind of spread out in such a nice way. You can convince yourself, and that's an exercise, that you actually the determinant of such a 3 by 3 would be 1 or -1. And it cares, of course, if the dimension is if the dimension is not 3, if it's less than 3, if you're picking 3, so there's a tag along in there, then then the determinant actually ends up being 0. You can see that by Smith normal form has a 0 column, and determinant of that is 0, and um, and that would work out as well too, but the properties of determinant. So we have so really let's have 0 if it doesn't work, 1 1 or -1 if it does work. So even if we were just like to take all the different submatrices and all the ones that do produce spanning trees, just put a 1 on, just take the absolute value of that determinant or square it or something like that and add them together. That'll actually be the exact number of spanning trees. But if you recall, the way that we found like the area of like a parallelogram or like a higher dimensional area or volume or something like that between different vectors was using this idea. This is like a generalization of Pythagorean's theorem, where we take so we could just take the matrix B, which is kind of like the incidence matrix with 1 row chopped off, and then you take it times its transpose, and it'll be a square matrix, and you do it in a way to get the smaller square matrix out of it, not the bigger one, the smaller one. And you take the determinant of that, it'll be the square. So it's not it's taking a square root, you square it, so you're not taking a square root. So basically you're just going to be adding your ones together, and you do end up getting 8. So if you don't want to go through all the submatrices, what you can do instead is you can just multiply these two guys and take a determinant, and you're done. And that'll be the exact number of spanning trees. Is kind of a fun idea. This is a theorem called Kirchhoff's theorem. Okay, so here's an example. Find the number of spanning trees. We cut off the one of the rows. We have a matrix. Then we take B times its transpose. It's a 4 by 4 matrix. Okay, the other one's an 8 by 8. We don't want the 8 by 8. We want the 4 by 4. We take the determinant of the smaller one, and we get 34, which means there's 34 different spanning trees for a graph that has this as its incidence matrix. Kind of a neat application of incidence matrices. We can actually count the number of spanning trees quite well just by chopping off a row, taking this times its transpose in the way to produce the smaller square matrix. Take the determinant of that, you have it. It's kind of a fun idea. Thanks for watching.